Hello. In this video, we're going to be looking at the upper and lower bounds for zeros. So essentially, this theorem is sort of hard to state, but it's a little bit easier to interpret, luckily. So we're going to assume that we have a polynomial with real coefficients, a positive leading coefficient, and a degree greater than 1. So what we're going to do is we're going to try to find two numbers, a and b, that all the real zeros lie in between. So a is going to be a negative number, b is going to be a positive number, and we're going to use integers for our software. So we're just going to be looking at between two integers here. So what it says is no real zero of f is larger than b, so that's going to be an upper bound on the real zeros if, when we divide by synthetic division by that zero, that possible zero, we get no negative numbers in the result. And we'll sort of explain that a little more in just a second. So we'll say that b is an upper bound of the zeros if the quotient and remainder have no negative coefficients when that's divided by the potential zero. Now we're going to be looking for a lower bound. So no real zero of f is smaller than a, so a would be a lower bound on the zeros if the last row in synthetic division of that function by that factor has entries that alternate in sign. Now notice that zero can be used as either a positive or negative number as necessary. So if we want it to be a positive, it can be positive. If we want it to be negative, it can be negative. So now let's try to interpret this theorem with an example here. And I'm using the same example that I used for Descartes' law of signs. I'm using the polynomial x cubed minus 6x squared plus 3x plus 10. So essentially, if we're looking for that upper bound, we're trying to find that if I divide this polynomial by a certain positive number, there will be no alternating signs. So this really, here's the negative that we need to think about getting rid of. So I told you this theorem was sort of an art, but really, with this part where we have an upper bound and we don't want alternation in signs, really all we want to do is make sure that that's negative is gone. If that negative's gone, then these will still be positive. So what I'm going to do is I'm going to write the coefficients of the polynomial down here. And if I want this -6 to be gone, if I want that negative to be gone, what I'm going to do is I bring down my 1. If I multiply by 6, that is going to add to the smallest number that can be positive. Remember, 0 can be positive or negative. That's why I chose a 6. So if I chose anything smaller than that, I'm going to still have a negative there. That's not what I want. If I chose anything bigger than that, I would have an upper bound, but it wouldn't be the smallest one. So I go ahead and divide. I bring down 1, multiply, get 6, add, get 0, multiply, get 0, add, get 3, multiply, get 18, and add and get 28. Now look at our resulting polynomial. It contains no negative numbers. So we have the quotient and the remainder have no negative coefficients when it's divided by that. So now we know that 6 is an upper bound on all the zeros. So all the zeros of this polynomial have to be less than or equal to 6. Again, it's not saying 6 is a 0 because notice we have remainder 28, so it's not even 0, but it's an upper bound. So this sort of gives us bounds on zeros. To find the lower bound is a little bit more tricky. So what we want to do is make sure this alternates in sign when we divide. So we're looking for a negative number now, a number that's less than 0. Then when we divide this polynomial by it, it's going to switch positive, negative, positive, negative. So I'm looking at this -6, and if I start bringing a 1 down, I need to essentially make sure that this is big enough that this stays positive, but when I multiply this by the number, I get a negative over here. That's what I'm looking for. So I'm starting with -2. I bring down 1, multiply -2 times 1, that's -2, add and I get -8. Multiply and I get 16, add and I get 19. Multiply and I get -38, and add and I get -28. So notice this is a bound on the zeros. It's a lower bound. but there might be a better estimate. So let's go ahead and try -1. So that's sort of the trick I play. I try to get closer and closer to 0 with this working. So if I try -1, I bring down 1, multiply, I get -1, add -7, multiply, I get 7, add, I get 10, multiply, I get -10, and I get 0. So notice this not only is a lower bound because I've got plus, minus, plus, and the 0 can be counted as a minus, so it alternates in sign, but also I found a 0. So this did help me find a 0. So all the zeros are between this -1 and this +6. And again, this will help us eliminate some of the choices. So if I go over here on my calculator, I've already got this typed in from our last video. I'm going to enter that in and graph it. You can see again that you do have all these zeros within that bound. So 6 will be over here, and -1 will be, of course, where that 0 is. If I trace and just go through, so we know that -1, enter, is a 0. It looks like there might be one at 2. Yep, that's definitely in between there. And 1 at 5. Yep, so 5 is a 0 as well. So all those zeros lie between -1 and 6. So those are the bounds on the zeros. I hope this has helped. Thank you.